Welcome to the demonstration corner. Today we're going to talk about thermal effusivity standard 798421, basically on its use in efficacy. So this is more of a conversation, I guess, and rather than a series of measurements, which we are involved in these measurements, but I think this is a worthwhile topic to just have a few discussions about. So first I printed off the standard 798421. This is available on the ASTM website. It's around $60 US. I encourage you to purchase it and read it. But what I can read is what's included on the website for information, which is the scope and the significance and use, and basically talk about the use of this standard for measuring textiles and how it relates to its use in textiles and or if it applies to other areas. So the test method covers quantitative measurement of thermal effusivity of woven, knitted, or non-woven fabrics using a modified transient plane source. Significance and use. This test method measures the rate of heat transfer or transport between a heating element and a fabric specimen. Some of the comfort properties of a garment relate to initial sensations that are cold or warm feeling, where lower effusivity indicates a sensation of warmth, or rather coolness, and higher values indicates a sensation of coolness. Let me read that again in case I messed it up. Lower thermal effusivity values indicate sensations of warmth, while higher values indicate sensations of coolness. The thermal effusivity of different fabrics and their initial perceived temperature are important to its assisting development of fabric selections. So, first I want to talk about that word quantitative, how it fits to the standard, and what we're replacing with the use of this standard is a skilled individual that is actually sensing a feelness of coolness or warmth. So I've been to a number of companies, been involved in thermal physical properties and related properties for 20 years. This was what was done to simulate a hot day. That person would sense how materials feel to the touch under a heat lamp for a hot summer day, or in a chilled environment for cooler temperatures. So the quantitative is describing a numerical representation of replacing that individual that would just feel something. So if you're going to engineer a material to feel more cool or more warm, you certainly want a numerical representation of that sense of coolness or touch to be able to develop materials from starting point, middle point, and end point, so you can see as you approach your goals, as well as an industry measurement of that same, so that if people are looking for a certain sense of coolness, they can reference the standard and the numerical representation of that coolness. That is where quantitative, that word quantitative, drops off. It really is of no more use in just describing that you're replacing the sense of touch by a human. So the other thing to point out from this standard is the effusivity range. Effusivity range is 35 to 1700 units of effusivity. I have some materials here just laid out sort of to share a point. This is XPS. It has a thermal effusivity of around 35 units. Cotton and other synthetic materials, all the way up to water, which has an effusivity of around 1600 units of effusivity. So this covers the range, and if you, of course, add moisture, whether it's sweat, wicking, or rain, to any one of these sort of fabrics that can soak that up, you're going to get higher effusivity than their intrinsic properties. And then you have phase change materials that's mixed in there. So that range of effusivity covers the applicable types of materials that one would want to measure a sense of coolness, at least in terms of the committee that developed this standard to replace that sense of touch person that was doing it with their hand, that sense by an individual. So what that means is that the committee that developed this standard is D13, and that is the committee on textiles. That's not a committee on any other composite, polymers, metals, or any other variation. That subcommittee is really interested in solely replacing and bringing value a numerical number for that sense of touch. So that's where I thought that quantitative was important. If you were to use, and the method that's mentioned in here, modified transient plane source. That keyword is transient, and why that quantitative word fits no further than what's described in the standard for the measurement of touch, sense of touch. Transient methods, measured in any other material type, standard, the assumption of transient methods, all of them, whether it be transient hot wire, transient plane source, other variations of those or modifications of those, the assumptions that are the materials you're measuring are homogeneous. That's a massive assumption, and the larger the degree of heterogeneity, the more error you have in your measurement by those methods. There is one rule of thumb or one practice when using transient methods to measure heterogeneous materials, and it's to measure longer test times with a larger sensor, depending on if your instrument has that diversity, that capability of varying test time and sensor size. The approach to trying to get as good measurements as you can with your method is to measure longer test times and use a larger sensor so that you measure more of your material. So, why am I commenting on that? Is because the test times that represent initial contact of feel, whether it's coolness or warmth, are 1 or 2 seconds described in this standard. So if you look at all the materials that are generally measured as a textile or fabric, they're all heterogeneous. So by the very assumption of transient methods, that's broken. That degree of heterogeneity is going to affect your measurements in a way that is hard to quantify. So that breaks that word quantify when it's measured. Measuring anything other than how does it feel and put a numerical number to that so somebody can develop more materials and compare it to that other number. So using transient methods to measure, so summarizing again, using transient methods to measure anything other than what's described in the standard, there are certain practices described in other standards that make that standard suitable for what is described in that standard, different than 7984. So with a test time of 1 or 2 seconds that's described in this standard, that massively increases the sensitivity to that assumption or breaking that assumption. So if you test other materials with that assumption that you can just extend its use, that would be a misleading sort of thought approach to how to measure those materials. So basically by describing that, the D13 committee has never reviewed or approved any other use of this standard for anything that's else described here. So I mention that because this standard does show up in reports for thermophysical properties, thermal conductivity, and interrelated properties. This standard shows up in papers for measurement of thermal conductivity. This standard shows up in other types of marketing and sales documents that are describing thermophysical properties like thermal conductivity, diffusivity, and specific heat. And it is true that thermal effusivity is the square root of thermal conductivity, density, and heat capacity, but it is not in any way related to the standard, basically. So thermal effusivity is the closest combination of properties that describes the phenomenon that you're feeling when you measure, the measure of that sense of touch or coolness. It's the closest thing they have, but it is not an actual accurate technical use of that term, thermal effusivity. It's just the closest thing. It's the same thing when we describe thermal conductivity of a highly porous insulation. Of course, thermal conductivity is referring to a solid where the only mode of heat transfer is thermal conductivity. In a high porous foam that has high porosity, you have effects of convection and radiation, and we're using that terminology loosely, but of course the proper terminology would be measuring that by thermal resistance and referring to the properties as thermal conductance. So thermal effusivity has been used to sort of as the closest combination of properties to describe this, but outside the use of this, that is a very dangerous use of that word, especially when you're referring to how this is measured, test times of 1 and 2 seconds, and the very nature of the standard describing its use on heterogeneous materials, where in any other situation, transient methods, especially short time scale, would make that a very dangerous measurement and very, very easy to generate erroneous data. So I wanted to just sort of touch on those things. So if you're considering thermophysical properties outside of textiles, and even if you actually want to measure thermophysical properties of textiles and not just the numerical representation of the sense of warmth or coolness, there are other methods that are better designed. So if you want to use these numbers in simulations, if you want to use these numbers before on specification sheets, that they represent an actual accurate the true numbers of what these materials are, there are ways of measuring them. And I encourage you to check out other standards. So one way to sort of associate how much weight has been put on thermal effusivity in its relation to any other properties or any use of it beyond this is really look at the number of pages. Let me describe that further. 789421 is 5 pages long. Of course, there's some diagrams in here, and the back page has some appendice type of information. So it's a useful document in that. But if you look at 3 of the most popular standards and the weight of those and how much description is needed to properly use them for what the standard is describing, how they can be used, you can get an important comparison. So ASTM C518, which is used for measuring insulation. It's part of that committee for insulation. And there's ISO equivalents. It's 15 pages long. And that is a very narrow range of thermal conductivity. So that number of pages is what is required to describe the method properly so that the user has a very good understanding of how it is used, the types of assumptions and potential errors that can keep them away from generating erroneous data. 15 pages for C518. ASTM E1461, of course, there's an ISO equivalent of this. This is the laser flash, very popular method for measuring a wide range of thermal conductivity of materials. This is 11 pages long. And again, this describes in detail several aspects of the measurement that are key to understanding so that you don't generate erroneous data. And then lastly, the transient plane source, which is what this is described as a modified version of that. Of course, that's another discussion. But the transient plane source, which is an ISO 22007-2, this is 20 pages long. So this describes in enough detail that if the user of a method were to buy this, they can generate good data and understand the assumptions of the approach and how that can impact negatively or erroneous data on their own materials. And I guess I forgot to mention the ASTM for laser flash is 1461, in case I forgot. So there's 3 standards, and they all have ISO equivalents, if I haven't mentioned them, that are significant number of pages to be able to properly describe their use, and their importance in the industry is there, and it's represented in publications. And these have been reviewed by the committee that's responsible for them for the efficacy of their use and making sure that the description inside is sufficient enough to properly use them. We want to make sure any standard that's describing thermophysical properties for anything other than a numerical representation of something cool or warm, we want to make sure the standard describes that, because the standard should have enough information to keep the user on a path of good measurements, not just simple. But again, 7894, if you look at its purpose, numerical representation of coolness or warmth, that's okay. It's just we want to make a distinction between the two. So I encourage you to, if you're considering thermophysical measurements, look at all the standards, and these are just a few. There's dozens of standards that are available depending on your material type, the size, the temperature range, which property you're interested in measuring, whether it's homogeneous, heterogeneous, isotropic, anisotropic. And all of those variables should be part of a conversation. And the question, any user of a method, whether it's a supplier of an instrument or the standards, you should expect to see what are the potential assumptions or errors that I can run into, and how can that affect my data. We certainly practice that. We want to have conversations and ask a lot of questions, and that's why we have so many methods sort of in our demonstration corner. And again, if you look at some of our other demonstration videos, you'll see we review those. But in addition to what we have here, we probably have about 13 different methods of understanding, rather of measuring thermal physical properties. And that's important understanding, even if it's not a method we're involved with, it's important to understand what is the proper method, even if we point them somewhere else. So hopefully that is useful, and I encourage you to buy this standard. It's available on ASTM. The 7894. We'll put some links below. If there's any questions on the use of 7894 in relation to its described purpose and intent, whether it be can we remove thermal conductivity, or any other interrelated property from thermal effusivity, I encourage you to read this because it does shed light on that and what I'm describing. So if it's a numerical representation of coolness or warmth and it's breaking all the assumptions of a transient method, can you really pull thermal conductivity from it in this application? Of course not. If you measure these with resistance, thermal resistance, you're going to measure it properly, and any of those effects that are between the two plates are going to be mature, those heat transfer phenomenon that you see. Of course, they won't be true. So if you try to use that data in a simulation or in development of that material where you're expecting the values to be true, you have potential for erroneous data. I encourage you to purchase a standard, review it, and compare to other standards. The significance of cost of these documents are small compared to the purchase of an instrument or the improper use of a method. Both for developing new materials and the total cost of a project, and use of this data on a specification sheet, a testing report, or any other document that will affect how people perceive the data that's generated, whether that's internal or external. That's it. Please feel free to get in touch with us if you have any questions, and we'll put links to these standards and how you can acquire them. And if you would like to discuss any of these particular methods, please get in touch with us. Appreciate the time. Thank you.